Welcome to Astro101, the Sun and its Neighbors. I'm Professor Bart Netterfield. This is the second of our 2 lectures on the terrestrial planets. The terrestrial planets are, of course, Mercury, Venus, Earth, Mars, and, of course, Earth's moon. We recall from the second lecture and from last week that the terrestrial planets are all characterized by being small, rocky, with a relatively thin or no atmosphere, few moons, and made from heavy elements, rock and metal. Last class, we looked at the surfaces of 2 of the terrestrial planets in particular, Mercury and the Moon, and recalled that Mercury and the Moon are both covered with many craters. We looked at what a crater is. It's when a planetesimal strikes the surface of a planet, maybe an asteroid or some other object. Typical speed of these collisions is very high, something like 100,000 kilometers an hour, maybe 50,000 kilometers an hour, somewhere in that range. The collision vaporizes the rock and creates an enormous explosion, and that leaves a crater. We, though, question the fact that there's not enough planetesimals around in orbit of the Sun. We kind of know the rate at which craters are created currently on the Moon, and there's not near enough planetesimals currently in the solar system to explain the number of craters on the Moon. And we also need to explain why there are so few craters on Earth, Mars, and Venus. We answered the first of those 2 questions, but not the second. The answer to the first one is that there were far more planetesimals early on during planet formation, early on in the solar system. Because basically planet formation was when all these smaller rocks collide together to form the larger ones. And so early on in the solar system, there was far more planetesimals to collide than there are now. So that early period of lots of collisions is called the heavy bombardment, and that is when most of the craters on the Moon were formed. It ended about 4 billion years ago, so the rate of crater formation now is far less than it was 4 billion years ago. We also noted that while Mercury and the Moon are largely covered in craters, there are some spots on the Moon where there are not craters, the so-called mares on the Moon. You can see one here. And so we needed to understand what caused that. Something had happened here after the heavy bombardment to erase the craters. That is the basic point. In order to explore this, we decided we need to look inside the Earth. And we talked about how you can do that using earthquakes and sound waves traveling through the Earth. And the timing and the amplitude of sound waves can allow us to peer inside the Earth and discover what the interior of the Earth looks like. We concluded that this is what the interiors of the planets look like, with the Earth having a solid inner core, a liquid metal outer core, and then going from very hot mantle material up to cool magma material and a core around the outside. The Moon, on the other hand, has just a core and cool mantle outside of it, and then Mars has a core and then cool mantle outside of that. These planets, Earth, Moon, and Mars, have all been measured with seismometers, those sound waves traveling through them. That was possible because we've landed probes on all these 3 planets. Mercury, we've never landed anything on Mercury, so everything we know about its core is based on its density from spin rate variation and from spin rate variations. Venus, just measured from density. It turns out to be extremely hard to land on Venus, although it has been done. So just a reminder, the crust is this low density rock that's floated to the surface of the planet, and the mantle and the core are higher density rock. They've sunk down. So the highest density is the metal and the metal core, nickel and iron, and then lighter is the mantle, which is made up of dense rock but not as dense as metal. Okay, we came up based on that on an explanation for what happened with the mares. We started out with a fully cratered surface. Then, at some point, late in the heavy bombardment, a very large object impacted the Moon, creating damage to the lithosphere. That caused molten rock to leak out from the mantle, and it turns out that melted magma from the mantle is fairly low density. Very low viscosity. It's very runny. So it came out and poured and filled in all the valleys, and you end up with this, these mares today. It left a smooth surface, and since then there's been a few impacts. So when you look at a mare, you see some impact craters. That indicates that it happened a long time ago, but not a long, long time ago. So sometime at the very end of the heavy bombardment, while the moon was still hot. Mercury also has mares. Mercury's surface is not as craters as the moon, which kind of indicates that Mercury probably cooled a little bit later than the moon did. So the Earth's moon and Mercury are covered in craters. So we could ask our question, what about Earth, Mars, and Venus? Are they covered in craters? They also went through the heavy bombardment, so we might expect that the Earth, Mars, and Venus would have just as many craters. Let's first go in with an instant quiz. Before we get onto that, thinking about this, which planet, Venus or Mars, would you expect to have more ongoing volcanism? Which one would you think would continue to have more volcanic activity, Venus or Mars? So thinking about that for a second. You can pause it if you want to. I won't wait any longer. Well, for volcanic activity, we need heat. We need the planet under the surface to be very hot, at above the melting temperature of rock. But we learned last week, and it makes sense, that smaller planets cool more quickly than larger ones. Mars is clearly smaller than Venus, so we would expect that Mars would cool more quickly than Venus. So Venus should have more ongoing volcanism than Mars. That would be our expectation. So the answer here is A, Venus, because Venus is larger and it cools more slowly. Okay, well, let's look at craters on Earth. This is probably the best looking crater on Earth. It's the Meteor Crater in Arizona. It was caused by the collision of a nickel-iron meteorite. It was about 50 meters across, and it was traveling at around 47,000 kilometers an hour when it impacted the Earth. So it's a pretty large object. 50 meters is pretty big, and it was going 47,000 kilometers an hour. And that was about 50,000 years ago. Now, in terms of planetesimals colliding, you could have collisions which are much, 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 much larger than 50 meters. So this is a pretty big one. It made a nice big crater, but not enough to wipe out life or anything. It happened about 50,000 years ago. It's not the only crater on Earth. This is a map of all of the craters, all of the known craters on Earth. There are about 190 that have been found on Earth. We noticed that there's a much higher density of them in North America and Europe and in Australia. That is more to do with the fact that that's where geologists who are looking for craters are, than it is that those are places where there are more craters. Although places like the Himalayas and the Rockies should have wiped out all the craters. So that's not super surprising, but nonetheless, this is probably a selection effect. It's not that North America had more craters, it's just that there's more geologists looking for craters in North America. Most of these craters are barely visible. In fact, Meteor Crater is fairly rare as being one that you can just walk up to and see, oh, look, there's a crater. Most of the craters you can barely see. In fact, you might only be able to see it because of using, plate tectonics to peer under the Earth looking for the density changes due to a crater or something like that. Most of these, relative to the heavy bombardment, are fairly recent. Obviously, this one is only 50,000 years ago. The oldest ones here maybe are 200 million years ago, and they're basically invisible. All but the very youngest show signs of very significant erosion. This one shows signs of erosion, but not very significant. But most of these old ones, the ones that are millions of years old, you can barely see anymore. They've been eroded away. All you can maybe see it is from the density changes in the rock or things like that. The oldest ones, as you can see, are extremely large, like these ones here, which are a couple 100 million years old. They're enormous, but not really visible. This crater right here, this one right here, was 70 million years ago. It's thought to be the impact that killed the dinosaurs. The way it worked is it kicked up tons of dust into the atmosphere, blocked out the sun, killed all the plants, and then all the large animals starved. Kind of sad. Okay, or good for us, I guess, who knows. None of these craters are from the heavy bombardment. The oldest ones are much less than 1 billion years. So, yeah, so there are craters on Earth, but not very many, and they're mostly been worn away by, well, by what? There are also craters on Mars. So here's a picture of Mars, and here's a crater, and there's a bunch of craters, and there's some small craters. There are craters on Mars. In fact, there are 384,343 craters larger than 1 kilometer across on Mars. We've had probes orbiting Mars. We've mapped the whole planet. We've counted the craters. That's how many there are larger than 1 kilometer on Mars. The moon has 13 times as many per surface area. That's a lot more. Right? When you look at this, like there's a lot of room in between craters on Mars. On the moon, that's not the case. Remember, on the moon, other than the mares, the craters are like continuous. Craters on top of craters on top of craters. On Mars, there's a lot of craters, but there's fewer than on the moon. Also, we notice that most of the craters are not as well defined as they are on the moon. Like they've been worn away a bit, maybe filled in with dust or something like that. Nonetheless, Mars has craters, but like 13 times fewer per area than the moon does. So that's something we need to understand. How about Venus? Well, there's a problem with Venus. As you can see, the surface of Venus is covered by a thick, permanent global cloud layer. That's it. It's never not cloudy. You can never see through it. It's the whole planet all the time. So how do you measure what's going on Venus? The first thing was this incredible series of probes sent by the Soviet Union between the 1960s and the 1980s. They sent many probes to Venus. Many of them were failures because of how hard the project was, but many of them were successes. And most of what we know about the surface of Venus in terms of its atmosphere and environment was from these incredible series of probes. Here is a picture from the surface of Venus from the last one to land on Venus. So what do we see here? It's like rocks, no signs of erosion, just volcanic pieces of rock. No signs of erosion, no signs of anything, no signs of cratering, at least if you looking at the camera here. But are there craters? What else do we learn about Venus? Venus has an atmosphere of 92 bar. So our atmosphere is 1 bar, so it's 92 times higher air pressure than Earth. That's a lot. It's enough, there's enough air, it's not air, it's carbon dioxide and sulfuric acid and some other things. There's enough atmosphere on Venus that if you were to like jump out of a plane on Venus, you wouldn't need a parachute. The air's thick enough to keep you from hitting the surface too quickly. In fact, that was a problem with some of the early probes to Venus. They had parachutes and they didn't make it to the ground because they just got going down too slow. The second thing is that the surface temperature is 464 degrees Celsius. I mean, that is extraordinarily hot. That's hot enough to melt lead. That's much hotter than your oven can get. The surface of Venus is incredibly, incredibly hot. And on the other hand, the wind speeds are very, very low. It's incredibly hot, but also very, very calm. What we didn't say here is also the atmosphere is acid. So, well, acid mixed with carbon dioxide. So it's a very, very, very nasty place. So when you're trying, one of the things that makes exploring Venus extremely difficult is no electronics works at that temperature. 464 degrees is far too high a temperature for any current electronics to run at. And so the only way you can make it work is to insulate the electronics, but eventually they're going to overheat because you can't cool them. So what they had to do is try to put the electronics inside of a insulated box, and they were able to keep the electronics working for about 52 minutes, which is actually quite impressive given just how hot it is outside on Venus. Anyways, that's the surface of Venus. That's one little spot You can't really tell what the whole planet is. So in the late 90s, actually early 90s, from 1990s to 1995, the NASA probe Magellan orbited Venus, which seems like kind of a silly thing to do since, I mean, it's all cloud cover, so what are you going to do, look at clouds? Well, it turns out that radio waves can make their way through clouds, at least if the right wavelengths. So Magellan was actually a radio mapper. And so it orbited Venus and made a radio map of the entire surface of Venus. So this is a picture of the entire surface of Venus. It's got both the height and the reflectivity. So these bright areas are where the rock is more reflective. The dark areas is where it's more absorbing. And then they were able to measure the height. So we have a complete 3D map of the surface of Venus. It turns out there are around 900 impact craters on Venus. So compare that to 100 and some on the Earth and 300,000 on Mars, or millions on the Moon. But of these 900, which is a tiny number, on Venus, there's no signs of erosion. They're all pristine. I guess that makes sense, right? Because there's no erosion, there's no wind to speak of on the surface of Venus. But there's only 900. You might say, well, the reason the Earth doesn't have any craters is because the erosion has gotten rid of them all. But it hasn't gotten rid of the craters on Venus, and there's only about 900. So that's interesting. The explanation would be that the entire surface of Venus is like a mare, except a recent one. The surface must be only somewhere between 300 and 600 million years old. Something around 300 to 600 million years old must have completely reset the surface of Venus, erased everything and started over. Well, what is it that's causing the surface to be turned over or reset on Venus so that we don't have lots of craters? Now, we expect there to be some volcanic activity on Venus because Venus is about the same size as the Earth. The Earth has volcanic activity. Presumably, Venus would too. Remember the story of how we got rid of the craters on the Moon in the mares? The crater-free mares on the Moon appear to be from volcanic activity, which has ended some 4 billion years ago. So 3.5 billion years, some number like that. So then the question is, what's causing? There must be much more recent volcanic activity on Venus for there to be so few craters. It turns out that Mars has many volcanoes. The largest volcano in the solar system is Olympus Mons on Mars. It's this giant volcano here. That's a picture of it from space. But there is no ongoing volcanic activity on Mars. It seems that volcanic activity on Mars ended billions of years ago. So there was a time when there were lots of volcanoes. So presumably there was a period of time when there was a lot of volcanic activity that may have erased many of the craters on Mars. But it was early enough that we still have billions of years of craters that have accumulated on Mars, just 10 times less than we have on the Moon. The Earth has many volcanoes. This right here is Mount Erebus in Antarctica, and that is a volcano. This is a picture of one of the experiments that I have done from Antarctica, and we'll talk about it in one of the later videos. But this is Mount Erebus, which is an active volcano, and you actually have steam coming out of the volcano there. The Earth has many volcanoes. There's definitely active volcanic activity on Earth. So, if there's volcanic activity on Earth, presumably there should be on Venus. Well, Venus does in fact have many volcanoes, and there appear to be some that are still active. However, the activity of the volcanoes on Venus doesn't seem to be enough to reset the whole surface in 300 million years or 600 million years. So the thought is that Venus must go through periods of intense activity and it's not a particularly well understood phenomena. We think that something happened between 300 and 600 million years ago that reset the surface. Probably has something to do with volcanic activity, but that's kind of as far as we can really go. Okay, remember the role of planetary size? Small planets are cooler because smaller planets cool quicker. So there's a the mantle will be relatively cool and solid, not much going on. So there'll be very little activity on the planet, nothing to erase craters. Craters just pile up since the heavy bombardment. A large planet, though, will still have, it's still hot enough, especially down the core, but it's still hot enough that you can get convection going. And so you can have the cold dense rocks gradually sinking and the hot, light rocks rising, producing convection cells, bringing heat to the surface and causing volcanic activity. So we expect the larger planets, we've said this before, the Earth and Venus, to have ongoing volcanic activity, which they do, and the smaller planets like Mercury and the Moon and Mars to no longer have volcanic activity. We expect it to have ended first on the Moon, then on Mercury, and then on Mars. And the age of the surface seems to go along with that. So that's pretty cool. So the biggest thing that deals with resetting the surface of the planets appears to have something to do with volcanism, or in general just the motion of the heat coming up from the core to the surface and changing the surface. So volcanoes, this molten rock from the upper mantle, makes its way to the surface. So this heat is brought up, makes a little puddle of molten rock in the upper mantle. It makes its way through cracks to the surface and comes out, and you have these, rivers of lava and things coming out, covering the landscape and also creating new mountains, or in some cases new islands, like is happening in the Pacific with Hawaii. All right, so volcanism. Earth's moon, the smallest. It cooled fast. Volcanism ended quickly. It ended right after the end of the heavy bombardment. And so there hasn't been any volcanic activity on the moon for billions of years. There's also no atmosphere. So once you make a crater on the moon, it's there. Nothing to wash it away. And the craters are mostly not erased, except for on the mares, probably due to volcanism. Mars, it's larger than the moon, so it cooled later. So there was volcanic activity and things to cover over the surface of Mars longer. So it didn't start collecting craters until later. It's got a very thin atmosphere, and the early craters were erased by volcanic activity, most likely. The later craters, hard to say. Probably they've been smoothed off due to erosion from wind and dust. Venus, second largest terrestrial planet, it's still cooling. So there's extremely low winds. So most craters have been erased by volcanism. None of them have been eroded away. And so, again, we expect that somewhere between 300 and 600 million years ago, there was some sort of burst of activity that erased all the craters, and it's been fairly quiescent since then. That's something still to understand. Venus is still largely a mystery, hiding under its cloud cover with incredible temperatures that it makes it incredibly hard to visit. And finally, we have the Earth. It's the largest of the terrestrial planets, just barely larger than Venus, but it is larger. It's still cooling. There's winds and there's water, which affect the surface, and most craters on Earth are erased. All right, so what else can change the surface? It's not just craters. You also can have the surface changing because of thermal stresses in the atmosphere, or in the planet. So take a look at this picture here of the convection cells. So you have a situation where the hot rock is rising and the cold rock is shrinking. The hot rock is rising and the cold rock is shrinking. That's pushing the rock here toward the rock there. So you get these pressure bumps. This is the Appalachian Mountains in the United States. These are pressure ridges on Mars. When you have the opposite happen, so you have this for converging plates. You can have diverging plates where the rising material moves out, and the rising material moves out, pulling these apart, and end up making cracks instead of mountains. So we can get both mountains and cracks depending on where you are compared to the convective cells. Now, these were formed on Mars when Mars still had convective cells. Now it's done. They're locked in. They're never changing anymore. The Earth, as we'll see in a moment, it's still active. Mountains are still changing. So it turns out that the crust of the Earth is broken up into what are called tectonic plates. These are all, you can see all these tectonic plates. Each of these is a separate chunk of rock floating on the kind of taffy very, very, very thick taffy mantle. So you shouldn't think of the mantle as being like liquid or even gooey, but it's rock that if you push it slow enough, it eventually bends and flows. So you have all these plates on Earth, and it turns out they're all moving relative to each other. The Earth's crust is broken up into plates. This appears to not be true for any of the other planets. There's no sign of plate tectonics really on Venus from the radar maps, on the Moon, on any of their planets. But it's true for the Earth, and we're not really sure why. There's a bunch of explanations. Maybe it's because of water getting in between the cracks and keeping them from fusing. Maybe the crust is different material. Maybe it's thinner. It's not clear why the Earth has plate tectonics and the other planets don't, but it's true. Earth's crust appears to be different than the other planets. Maybe the cracking is because of the Moon, but probably not. I mean, I think the answer is we don't really know why the Earth has plate tectonics. Again, it's another ongoing question of that's really interesting. Isn't it cool that physics hasn't answered every question yet? Okay, so let's take a picture of how plates are going to behave. We've got a plate here, maybe the North American plate, and we've got the Pacific plate, which is underneath the ocean, and we've got the European plate. We've got these convective cells. So let's think about a converging cell. In a converging cell, the Pacific Ocean plate is being pushed underneath the North American plate. That causes a range of mountains, the Rocky Mountains up and down the coast of North America, to be pushed up as the trench gets pushed down. It's because the convective cells are going this way and going this way. So going this way is pushing the North American plate that way. Going this way, it's pushing the ocean trench that way. The ocean trench, it turns out, is heavier and denser than the North American plate. So rather than just running into each other and buckling like this, it goes underneath and pushes up the North American plate. This motion completely recycles the oceans every couple 100 million years. So in fact, there are very few surviving craters in the ocean because the ocean floor is continuously getting replenished by this motion of subduction. The North American plate, however, is getting pushed up. So you get this line of Rocky Mountains, but it's not getting buried or anything. It's sort of more stable. So the continental rocks are more stable. They haven't been dumped underneath for billions of years. So you can have rocks that are billions of years old in North America. Here we have a diverging cell. Yeah, so ocean plate gets pushed under, continental plate gets pushed up, and you end up with the Rocky Mountains. For a diverging plate, where they're moving apart, you'll get these cracks, undersea ridges and cracks. So you have some pushing up to make it rise, and then the fact that they're pulling apart makes them cracked. And so you get these, you can see them in maps of the ocean floor, these sort of hills with cracks up the center, and that's coming from this diverging plates, the plates being pulled apart, but with new stuff coming up underneath. The Earth's mountain ranges are at converging plates. These are not volcanoes. This is from converging plates. Two plates, either an ocean plate pushing up the edge, or maybe two plates actually colliding, like in the case of the Himalayas. So, but they're not volcanoes. These mountains are not volcanoes. Now, there are volcanoes in the Rocky Mountains, but the vast majority of the Rocky Mountains are due to this collision of plates, not due to volcanic activity. Although when you have colliding plates, you're going to make cracks, and you're going to get volcanoes as well. So you get both. Okay, so the last thing that affects the surface of the Earth is erosion. You can get erosion from flowing water, from glaciers, and from wind. So here we have the Colorado River, which is flowing water, digging this giant trench in the Earth over millions of years. You can also have flowing ice, glaciers. So there was a time that, as we'll see next in our next class, but the temperature of the Earth changes radically over the tens of thousands or hundreds of thousands of years. And so you have periods of ice age where the whole Earth is covered with ice, and you have periods of substantial melting where it goes away. And during those periods, you can get these giant sheets of ice that can flow and cut cracks and dump material. And so glaciers created Yosemite Valley during the ice ages. You also can get wind erosion that can move move sand around. So these dunes in the desert are caused by winds blowing sand and then piling it up in piles in the desert. And then you can also have erosion where the sand is moved by the river. So the river digs up sand from the river, and when it gets to the ocean, it stops and dumps and creates deltas. All of these things are due to the flowing of water, ice, and wind. And these all can change the surface of the Earth. And so if you want to, so that is an important, so there's two major ways we're seeing here now that the surface of the Earth can be changed. It can be changed through volcanism. It can be changed through cratering. Through erosion. Also through cratering, but yeah. Okay. All right. So here is a picture of erosion on Mars. So this is a river valley. It's dry. It's dead. It's a former river valley. And here's a former delta. Okay? So this is an ancient delta. It's completely dry now. I mean, Mars is dry. But there's nonetheless a delta. It's like, oh, well, there was water flowing on Mars then. Maybe it's seasonal. Maybe if we wait, it'll come back. There'll be water on Mars. But notice, there are craters on the delta. So you have this delta, and then you have craters in the delta. Well, what would cause that? Well, it's time, clearly an excellent time for an instant quiz. What does the existence of craters in this dried river delta on Mars tell us? The river must have flowed around the craters. There must have been very recent bombardment on Mars, but not the other planets. The river must have dried up a very long time ago. And these are probably the result of an ancient nuclear war. I'll give you a second to think about it and try and pick your answer. You can pause it, so I can give you a long break. There, hopefully you paused long enough to answer the question for yourself. Let's think about it. The river must have flowed around the craters. Well, this is a crater going down. There's no sign of the river going up. There's no sign that the river went around the craters. No, the crater happened after the delta was formed, so that's wrong. Very recent bombardment of Mars, but not the other planets. So you have boom, 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 boom. A bunch of craters went over here. No, there's no way that you would, like if it's raining craters on Mars, it'll be raining craters on all the planets. There's no real way to have a higher chance of planetesimals hitting Mars and not the Earth. So we think that must be wrong. The river must have dried up a very long time ago. Well, yeah, that makes sense, right? Because you have a delta. The delta dried up and it stopped, and then a crater hits, and then millions and millions of years later, another crater hits, another asteroid hits, and then millions and millions and millions of years, another one hits, another one hits, and you end up getting a few craters. These are probably all formed hundreds of millions of years apart. This says that the river must have dried up an extremely long time ago, at least hundreds of millions of years ago, up to billions. So, water stopped flowing on Mars a very long time ago. So there was a time when Mars had flowing water, it had rivers, it had deltas, it had lakes and seas, but the water is all gone now. We'll talk about why next class. And now it's just all dry. And cratering has more or less stopped too. In fact, the Mars surface is now pretty stable, except for there's still strong winds in the extremely thin atmosphere, so you still get dust being blown around and very, very, very slowly eroding away the rock, but extremely slowly. So Mars is now pretty stable except the blowing sand. All right, so how do we change the surface of a planet? We talked about the 4 ways. High-speed strikes creates craters. So an asteroid, a planetesimal, something hits the surface of the planet. There's the explosion, creates a crater. That's method 1. Method 2, volcanism. Molten rock makes mountains and covers old surfaces. Method 3, erosion. Ice, wind, and water cut into surfaces and move material around. And method 4, internal stresses, plate tectonics, things like that, cause mountain ranges and some types of canyons. So that is how you form the surfaces of the planets. So today we've looked at how at what causes Mercury, Venus, and Earth to have far fewer craters Earth, Venus, and Mars to have far fewer craters than Mercury and the Moon. We understood this because the larger planets cool slower, and that means that internal stresses and volcanism can last longer, replenishing the surface. We've seen how on Earth, particularly, erosion also does an incredibly significant job in wiping out any craters, even recent craters. So next week, we'll be looking at the atmospheres of the terrestrial planets and what that all means and how it came to be. See you then.